We'll continue that last article. Now that was about the electromotive force. Now we have seen that the charge is moving through one complete cycle with the energy supplied by the electromotive force. Here, when the charge is moved through the one cycle, we say that the work is done on that cycle, the charge. And when we say that the work is done, we call it as dW. But work is done on whom? On the charge dq. So that it moves in the manner which is accepted, that is clockwise. Now here, when I want to write this equation of EMF, I have written that E is equal to dW upon dq, because small amount of work is done over the charge dq. Hence, work done unit is joule and the unit of the charge is coulomb. So SI unit of EMF is joule per coulomb. It is very simple. But only the thing is that we have to take into consideration that writing of formula. Then everything is easy. We can grasp it. Next is that now we are going to deal with the ideal EMF. Ideal EMF means what? It is very simple. We know that the cell contains internal resistance. But in case of ideal EMF, there is no internal resistance when the charge moves from that EMF. So here no internal resistance to the motion of the charge carrier, and therefore it is equal to potential difference across the two terminals of the device. Okay, getting what I want to say? This means that when no internal resistance, then potential difference, ideal EMF is equal to what? Potential difference across the two terminals of the device. Okay. Now next point is, practically it is impossible. Practically internal resistance is impossible. We cannot choose that zero internal resistance. So here when we say that current flows through a device, if I have an EMF device, that EMF contains internal resistance R, while the EMF is there, and this differs from the potential difference across the two terminals, that is V. So it is written as V is equal to E minus IR. No doubt, this is EMF, but the charges which are passing through that EMF, this means that again one EMF is created or it is formed across the internal resistance, that is IR. So by Ohm's law we know that V is equal to IR. We equate these two equations. V is equal to E minus IR with IR. So IR is equal to E minus IR. Now we take I term on the left hand side. On the right side, the remainder is epsilon E upon R plus R. So we have got the value I is equal to electromotive force upon R plus R. If I put this value R is equal to 0, according to Ohm's law, external resistance, if I select it as 0, the current will be maximum in the circuit, and its answer will be what? If you substitute R is equal to 0, we get I is equal to E upon R. So this is one of the way how ideal EMF and non-ideal EMF explanation is being considered. Now here we are going to see a new point, that is cells which are connected in series. Now you see in the upper half there are two EMF or two batteries which are connected having the values of 1.5, 1.5. Now you are very well familiar that what happens when you consider that two cells when connected in series will give a large value of voltage, but the current remains same. So in this situation, now since we are taking two batteries, therefore 1.5 plus 1.5 will give you 3 volt. And when I say that it gives 3 volt, this means that in series resistance, the equivalent series resistance Rs is equal to R1 plus R2. We call it as the voltage V1, I will call 1.5, V2 as 1.5. So total V is equal to V1 plus V2. Now total V is equal to 3 volts. This is the example. Now in such a situation, if you take large number of cells, n number of cells it will take, then the equation will have, because it will be the sum of the voltage of n cells, and therefore we write it as the summation of V1 means Vi, where I takes the value from 1 to n. So this is the case of the cells in series. Now when the statement when I will give you regarding this cell series, the equivalent EMF of a number of cells in series combination is the algebraic sum, that is summation. Already I had mentioned it, but what happens, we are unable to write the mathematical language into physics language, or into mathematical statement we are unable. So it is very simple. We say that the equivalent EMF, that is V or E, is equal to E1 plus E2 plus E3. Both the things are accepted. Now here, when I say equivalent EMF of a number of cells, it will be E1, E2 up to En, which will be connected in series. So result will be what? Algebraic sum of the individual EMF. So hence we have written as summation of EI, where I takes the value from 1 to n. Now there is also the important role of the internal resistance, small r, across this EMF, individual EMF. So we have to also take into consideration that the current is flowing through this internal resistance. And what is this product IR? It is nothing but again EMF only. So again I am adding the terms summation of IR. Now here we know that the current is constant. Then what will be the variable one? R term will be the variable, small r. It is written as R, I. Summation of Ri, I takes the value from 1 to n. So taking these two equations together, we come to the conclusion that this is the equation. Now you see here, V is equal to summation of EI. Okay. EMF, if you take n terminals, I is taken from 1 to n. But this EMF is having its own internal resistance. Current is constant. So current multiplied by summation of Ri, where I takes the value 1 to n. So we get this form of equation: V is equal to summation of Ei minus I into summation of Ri. Okay. So this was all about the cells in series. Now what are the advantages of the cells in series? They are given only two advantages. When you connect in series, it produces a large voltage, because I told you, if you take 10 EMFs, then the value will be how much? 1 EMF value, all the EMF are identical, having value 1.5. So 1.5 when you take for 10 numbers, you find that you will get 15 volt. Got it? So this means that the voltage value can be increased by connecting the number of cells in series. Next advantage is that cells which are damaged can be easily replaced. Now you have the example that we are, while using the torch at night, we are having those A4 size cells which are placed inside it. If any one of the cell becomes poor or weak, then you can replace it, and you can replace by a new one. So simple it is. So hence we say that it is an advantage. Now, all these things we have spoken regarding the cells in series. Now I want to take the final point, that is cells in parallel. Now when we take cells in parallel, you see here the figure it is. Here two terminals are there. Positive terminal of first EMF, second EMF is connected to B1, whose potential is VB1. Similarly, on the right side there is another terminal B2. The potential is VB2. Now, this circuit which you are watching, that is for the parallel. When we say that it is in parallel, now here we are taking only two cells. Now what will happen to these two cells? Now this, suppose across these 2 points B1 and B2, if I will consider these two EMF E1 and E2, what will be the resultant? What will be the answer for that? So for the first cell, we say that V is equal to VB1 minus VB2. What we have said? VB1 minus VB2, potential difference. Potential difference means this voltage minus this voltage. So that is called as the potential difference. Now, in this case, if we see on the, if we look to the first cell, then we get equation V is equal to VB minus 1 minus VB2. Now, previously we have proved this equation. We have, because our cell is having internal resistance, so we have to not neglect IR term. So we are writing it as V is equal to E1 minus IR1. This is for the first cell. You just, I'll go to this expression part. Now you see here. Now here, as earlier I have mentioned that V is equal to V1 minus VB2. For the first cell, it is E1 minus I1 R1. Because now here we are considering that this I1 is nothing but epsilon 1, yeah, E1, that is EMF 1 minus V upon R1. This equation we have got already, we have proved it also. But now similarly we have to take the values for both the cells. First cell we have got that I1 is equal to E1 minus V upon R1, because V is common. Now here you see that the combination was parallel, and according to the parallel condition, the voltage which is being given to the first cell will be the same voltage given to the second cell. This means that both are having the value V. Yes, and so when we say that there is a common condition for second cell also, V is equal to VV1 minus VV2. Again you replace it by equation E2 minus I2R2. Now rearranging this term, we get I2 is equal to E2 minus V upon R2. Now, in this case, in this circuit of parallel cell, we know that voltage remains constant but current is different. So for the first cell we say that the current is I1, and for the second it is I2, and sum of these I1 plus I2 is equal to total I. So hence, combining these three equations, we come to the conclusion that I is equal to EMF 1 upon R1 minus V upon R1 plus E2 upon R2 minus V upon R2. Now, slightly we are rearranging it. We are taking E term in one bracket, we are taking V term in another bracket. So finally we come to the conclusion that this V upon R1 plus R2 is equal to E1 upon R1 plus E2 upon R2 bracket calculate minus I. This is the mathematical part, simple part it is. Now, taking the LCM of the first bracket, we get V into bracket R1 plus R2 upon R1 R2. Similarly, in the second bracket, again we are taking LCM. E1 R2 plus E2 R1 upon R1 R2 minus I. Now, if you look here, on the left side there is R1 R2 product, right side also R1 R2 product, but this item does not contain R1 R2. So we multiply and divide it by R1 R2, and then rearranging it, we get V is equal to E1 R2 plus E2 R1 upon R1 plus R2 minus I R1 R2 upon R1 plus R2. So we have got the equation similarly as V is equal to EMF minus I into R. So here, if I replace these two cells by a single cell, then the connection between the two points B1 and B2 with EMF E equivalent and the resistance R equivalent will look like this. V is equal to E equivalent minus IR equivalent. So this is how, when we say that we have got this equation, we focus here, right side, that the two equations, first equation E equivalent, we have got it, R equivalent, we got it, then this R equivalent will be simplified like this, 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2. Similarly, we simplify E equivalent is equal to, here we are taking that as R equivalent, E equivalent upon R equivalent. Means what we have done? We have divided this equation with this equation, and finally we get E equivalent upon R equivalent is equal to E1 upon R1 plus E2 upon R2. So this was the equation for two cells. If I take n cells, n resistance will be there, R1 to Rn, EMF will be from E1 to En. Therefore, the 11.51 equation will look like this, and we have written in the equation 11.52, 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3 up to 1 upon Rn. What about this? When we take the or multiply this by 11.52 by E equivalent, we get E equivalent upon R equivalent. E equivalent means what? E1 to En. R equivalent means what? R1 to Rn. So this is all about the cells which are connected in parallel. Finally, the advantage is that in parallel circuit, the circuit will not break open even if your cell gets damaged, because damaged cell will not affect the circuit now. So that is the advantage. And disadvantage is that the voltage developed by the cell in parallel combination or connection cannot be increased by increasing the number of cells present in the circuit. So this was all about the cells.